I'm Nick, and I'm going to talk about writing programs that write other programs. And so technically, a program that writes other programs is called a program synthesizer. And so what it does is it takes this kind of formal specification that describes basically your desired program, and then it searches for such a program, and if it finds one, it will return one to you. So you might be wondering, why do I need a program synthesizer, and am I just too lazy to write these programs myself? And the answer is yes, but that's not actually how I got here. So let me digress for a bit and talk about compilers. So kind of the common things that we want out of an optimizing compiler are like, well, it's an optimizing compiler, so hopefully it has good code generation and our programs that we compile with it run fast. But at the same time, like, we're busy people, we have places to go, people to see, and so this thing should compile code pretty fast as well. But most of all, it needs to be correct, because otherwise everything else was useless. And if you want a fast compiler but you don't care about correctness, well, I can emit garbage like really fast, but that's not actually what you want, right? And so each one of these things is a lot of effort, but altogether this is really a tremendous feat of engineering to get all of them. So to really illustrate this, let's consider a peephole optimizer. So what a peephole optimizer does is it matches patterns of kind of known suboptimal instruction sequences, and then it replaces them with the better version, something that runs in fewer CPU cycles or has smaller code size. So for example, adding 0 to x is useless. You can just use x directly. So the peephole optimizer will recognize the pattern x plus 0 and replace it with x. Or x multiplied by 2 is the same as x shifted left by 1, but a left shift is generally faster to execute than a multiply in most architectures. So LLVM is a compiler framework that's used by the Clang C and C++ compiler, and it's used by the Rust compiler and a bunch of other compilers. And there are a bunch of engineers who work full-time on LLVM at places like Apple and Google. And the peephole optimizer inside LLVM has over 1,000 of these kind of pattern and replacement pairs. And so even half that many is way too many for me to write by hand. And some of these replacements aren't like easy to write either, especially to get them correct for like all the corner cases. So I need something that's kind of like a more efficient approach that doesn't require a bunch of engineers at like Apple and Google working on this, something that maybe I could do myself. And so if you kind of squint and tilt your head to the side, well, these patterns are maybe like specifications. And the replacements are kind of like mini programs that implement that specification and that they have the same behavior, but they're just also better in some way. So can I use program synthesis where I'm taking these unoptimized programs as a specification to find not just a better program, but ideally like the optimal program? And it turns out that kind of finding the optimal program has a name, and this is super optimization, because it's just like that much better than regular optimization. So the goal here is basically, can I like automatically and kind of mechanically create a peephole super optimizer via program synthesis? So here is kind of the language that we're working with. It's fairly low level. Each instruction defines a new variable, and then those variables are never reassigned. And each instruction has just one operation. So we have operations for like addition and multiplication, and we have bitwise stuff like XOR and AND. What we're not dealing with is like loops or function calls. This is just like straight line programs. But if we have 32 different operators, and we're synthesizing a program that's n instructions long, well, that means we have 32 choices for the first instructions operator. We have, well, times 32 instructions, or 32 operations that are choices for the second instructions operator, times 32 choices for the third instructions operator, et cetera, up to n. And we have an exponential search space. That's not good. With just a 10 instruction long program, which is really not able to do that much, we're already past the billions, we're past the trillions, and we're in the quadrillions. And this is just choice of operator, not even dealing with like operands yet. So brute force search is not really a good option here. But luckily, there's these tools called SMT solvers. And kind of fundamentally, what SMT solvers are good at is doing exponential search. Because it turns out that most of the problems that we want to solve aren't like the super, super hard cases. And so SMT solvers have gotten pretty effective in practice at exponential search. So what an SMT solver does is it solves a logic formula for you. And so in this case, say we have some integer x whose value we don't know, but we're kind of searching for the value, right? What we do know about it is that x plus 2 is 5. And we can ask the solver whether there is a satisfying assignment to the unbound variables, in this case that's just x, that makes all of these assertions true. And so in this case there is, and so the solver replies to us sat. And then once it does that, we can ask what those assignments are, and it tells us that x is 3 because 3 plus 2 is 5. So can we take our exponential program synthesis search problem and just give it to the SMT solver by translating it into a logic formula and then get an answer? Well, this is what program synthesis looks like as a logic formula. And I know this is fairly big and scary, but don't worry, we're going to break it down together. So there exists some program P. This is the program that we're searching for. You know, maybe there's multiple programs, but we're really just looking for one right now. And for all of the different variables I and O, basically when we run the program on those input variables to get the output variable O, then the specification should be satisfied. We're looking for a program that satisfies the specification for all inputs, because if there's some input for which the specification is not satisfied, that kind of like represents a bug, and we don't want a buggy program because that's not what we're looking for. So if we plug this formula into an SMT solver, are we done? Do we get an answer? And unfortunately, not quite, but because SMT solvers don't like to have these kind of nested exists and for alls. They really struggle with it, and it makes them go bleh. But hope is not lost here, because we have another tool in our toolbox, and this is counterexample guided iterative synthesis, also known as CGIS. And so basically, rather than asking the solver to solve the whole big nested exists for all problem all at once, we kind of decompose it into two different parts. And the key is that each of these two different parts is without nesting, which means that the SMT solver can solve each of these parts on its own. So the first part is finite synthesis. And finite synthesis takes kind of a set of examples. Here we have 17 and 42. And it finds a program that satisfies the specification just for those examples. And for other examples like 0 or 100, maybe the specification is satisfied, maybe not. We just don't really know yet. And the second step is verification. So it says, OK, given that you've synthesized a program that works for some inputs, are there any inputs for which this program is not correct? And if it can find one, we call that a counterexample. So in this case, we find the counterexample 16. And so we go back to finite synthesis again. And we say, OK, can you find a program that works not just for 17 and 42, but also for 16? And so we kind of repeat this back and forth over and over. And finite synthesis is going to generate more and more general programs as it learns more counterexamples, until eventually verification can't find any inputs for which the program is correct. There aren't any more counterexamples, which means that it's correct for all of the inputs. And well, this is what we were searching for, and we found it. So we're done. I don't have time to explain in depth like how finite synthesis and verification work. But the key takeaway is that CGIS breaks the problem apart into two parts that don't have the nesting and that solvers can solve. So I implemented CGIS in Rust with the Z3 solver. And here is an example of a synthesized optimization. We're rounding the variable a up to the next multiple of 4. And so we managed to shave off 2 instructions, and we also replaced expensive multiply and divide instructions with bitwise XOR and AND, which are a bit cheaper. And if you want to learn more about that, I wrote a very in-depth blog post about it here, and the source code is up on GitHub there. Please support the striking grad students if you can, and also shout out to our captioner Mirabai and all the AV folks. And that's everything. Thank you very much.